morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. And today, while listening to West End Girls by the Pet Shop Boys, we are talking about vectors and scalars. Let's get to it, shall we? Okay, so we have a nice opening problem here. An airplane is flying at 800 kilometers per hour due east. A cold wind suddenly blows from the southwest at 35 kilometers per hour, pushing the airplane slightly off course. How can we illustrate the plane's movement and the wind using a scale diagram? What operation do we need to perform to find the effect of the wind on the airplane? And can we use a scale diagram to determine the resulting speed and direction of the airplane? Because if wind is blowing, it's going to be pushing the plane in the direction it's blowing, at the speed it's blowing. And of course, the plane is flying at a speed, so what's the new direction and speed of the plane? We can figure all of that out using vectors. And a lot of this is going to be definitions and figuring out what is what. Quantities right here, which have only magnitude, are called scalars. Well, what in the world is magnitude? Well, magnitude is very simple. It's size. Geometrically speaking, magnitude is the same as length, distance, or speed, depending on the situation. So it's something that can be measured. Quantities which have both magnitude and direction are called vectors. So scalars just have magnitude, vectors have magnitude and a direction. The speed of a plane is a scalar because it describes its size or the strength. Like the velocity of the plane is a vector. It includes both its speed and its direction. Acceleration is a vector quantity, as is force, displacement, and momentum. And I just put this down here for your reference, again, the airplane. Oh, I love this one. Farmer Giles needs to remove a fence post. So if he's pushing on the fence post, he's using both force and direction. He has a choice of how much force and in which direction to push the fence post or pull it or whatever to remove it. We can describe that mathematically or model it mathematically using a vector. We can also represent a vector using a directed line segment or arrow. The length of the arrow represents the size or magnitude of the quantity, and the arrowhead shows its direction. Now, the length only represents its size if it's to scale. In this example, they're saying that the distance of 1 centimeter represents 25 newtons. So this must be 2 centimeters long if it's 50 newtons. For example, if Farmer Giles pushes the post with a force of 50 newtons to the northeast, we can draw a scale diagram. Here's a nice important note. If they say northeast, that is exactly northeast. We know this way is east, right? So exactly northeast is, I should say, northeast is exactly halfway between north and east. So half of 90 degrees, because this is a 90-degree angle between north and east, is indeed 45 degrees. So let's try an example doing that ourselves. Draw a scale diagram to represent a force of 40 newtons in a northeasterly direction. So let's just say we let, 1 centimeter equal 10 newtons. Okay, now you can sketch this, but if you have a protractor handy, then it'll work out nicely. Okay, 1 centimeter equals 10 newtons. Northeasterly is going to be at 45 degrees. So I need 40 newtons, so I'm going to need 4 centimeters. So I'm going to take my ruler and put it right there at the point and make sure it's going through 45 degrees. That's pretty good. And then I'll take my marker here and I'll put a point here and a point here, and then I'll get all this out of the way. Oopsie. And let's see, and I'll just draw my vector. Let me get my arrow tool here. Blue looks good. I'll start here and go here. And that is a vector of 40 newtons in a northeasterly direction. Now what I also might want to do is just show, north and east. There's east, here's north, and then we could label this angle right here 45 degrees and slap a north and an east on there. Okay. I guess we could write 40 newtons on here too if we wanted. All right. But since it's 2 centimeters long or 4 centimeters long and each centimeter represents 10 newtons, then it's 40 newtons. I think you get the idea there. That's not so bad. Vector notation, very important. Consider the vector from the origin O to the point A. We call this the position vector of point A because it tells us how to get to point A from the origin. And we can talk about it. Let's see. Didn't want to do that. Okay. So here's point O, and here's cap A, and there's lots of different things we can call it. Notice this little a here, and it's boldface. This position vector could be represented by OA with an arrow on top, or boldface little letter a is used in textbooks and on tests sometimes. I rarely see this with the little schwa thing over it. I rarely see this. Or little a with a vector on it, over it. A lot of times I'll just write it with a half arrow like that. The magnitude or length could be represented by these two vertical lines. And hopefully you're saying, hey, that's absolute value. Okay, fine, but if we're talking about vectors, it represents magnitude. So this reads the magnitude of vector OA. The magnitude of A. The magnitude, it's just putting those lines around that represents the magnitude. Okay, so let's get rid of that. Say we have vector AB. We say that AB is the vector which originates from A and terminates at B. Okay, and vector AB is the position vector of point B relative to A. In other words, it's the location of B as related to A. Okay, to get from A to B, it's the same sort of thought process. It's the position of B as compared to where A is. That's very, very important. Two vectors are equal if they have the same magnitude and direction. So all of these vectors are equal even though they're in different places. We consider them equal. This one could be way over here. Doesn't matter. If they're traveling in the same direction and they have the same magnitude, then those vectors are indeed equal. Geometrically negative vectors. Let's see. Vector A and negative A are down here, I guess I should have started here, that's okay, are parallel and equal in length but in opposite direction. AB and BA have the same length but they have opposite directions. We say that BA is the negative of AB and we write that BA equals negative AB. That's pretty much common sense there. So if they're going in opposite directions, then same magnitude, then they are negative vectors. Okay, and our last example, PQRS is a parallelogram in which PQ equals A and QR equals B. Find vector representation for all of these. So we're going to find vector representation for QP. Well, given what we have, I could write negative A is equal to, oops, sorry about that, QP. I don't have to write that QP thing, but I'm just writing it from here. Why? Because A is going in this direction. It starts here and goes this way. But if I turned it around, if I negated it, it would start here and go this way, which is what QP is, because Q starts at Q and ends at P. B, what about RQ? Well, that should be obvious, I think, from the first example. Same reasoning. That would be negative B, because QR starts at Q and goes to R, but we want to go RQ. So we start at R, go back to Q. That's the opposite direction of vector B, so that's why we write negative B. And then C, SR. So from here, starting here and going to here. Well, this is a parallelogram. That means opposite sides are parallel, and if they're parallel, they're going in the same direction. Remember what we said before. Vectors are equal if they have the same direction and magnitude. S to R and vector A are going in the same direction. They have the same magnitude because they're the same length, because they're opposite sides of a parallelogram. So I could call SR vector A. Pretty nifty, huh? And then what about SP? Well, SP has the same magnitude of B, but is going in an opposite direction because B starts here and ends up here. SP starts here and ends up here. So I could represent it using negative B. So that's going to do it. I enjoyed it. You enjoyed it. We all enjoyed it. With that, I am out!